left off. So we finished the link budget analysis. It kind of taught us how to dimension system properly. Essentially you see it's just like a balancing act. You have all the balancing and accounting act. You have to take all the gains and losses into account and make sure that the two links can talk to their appropriate receivers. Now, one component that we had as a part of the link budget that we so far just took as given was the fade margin, right? You never design a link so that it's stretched to the maximum. You always put some margin there so that in the case that something happens, your link still stays up. What can happen here? You know, when you're talking in satellite communication, you're talking over large distances, but really the variable part of that link budget is your path loss through the atmosphere. Because even though we say, well, we start with the free space loss, there's a whole bunch of stuff in before the signal leaves the atmosphere. And that it goes through the air itself, it goes through the clouds, if there might be raining, might be snowing, might be, you know, exposed to solar flares and all sorts of things that will add additional loss. Now the problem with that loss is not constant. It is random in nature, and it's also dependent on dependent both time-wise and space-wise, right? Different times of the day, different times of the year, you may have different losses, but also different locations in the world, you may have different losses as well. You know, as you know, climate changes throughout the globe, and the frequency of rains, the intensity of rain, and so on changes from a given lat long to another lat long. So how do we approach the design in those cases when you have to deal with these uncertainties? Well, there are two components to it. First one is you collect statistical data. You collect history of what happens at the given location, and you compile this into a set of tables, curves that are available to a designer. Where you actually say over this percentage of time you experience this kind of environment, right? So this is the data that enters the design. So that's the first component. The second component, we have to have statistical tools at our disposal so to be able to design for a given reliability. You're going to say, okay, I'm going to design this link so that it is up 99.9% of the time. That will translate through some math into a fade margin that you need to put in your link budget so that you can accomplish that design. To do all of this, we need some statistical tools. And what I had on my notes that I didn't bring them were some basic review of the statistical tools that we're going to use. I'm going to present three functions that we're going to be using. One of them is going to be cumulative distribution function, probability density function, and complement of the cumulative distribution function. So I need to kind of present those three curves because I'm going to be using them extensively through this part because they are essential tools for describing what we call random variables. And that loss that we're talking about is essentially a random variable that we need to take into account. So let me first define, let's X be a random variable. And let me define three functions that we'll use to describe this particular variable. The first function that I'm going to define is going to be cumulative distribution function. Simply called CDF. There's going to be quite a bit of notational abuse here. Proper way to write it would be CDF of the random variable x at a given point x0. But usually this x is removed and then whatever I put in the parentheses is actually the same as the random variable. So what does CDF of random variable x at a given point x0, how is it defined? It is defined as a probability that the random variable x takes values smaller than x0, right? So you can see that for any given random variable, you can supply the input to this function, and what the function will give you back is the probability that the random variable is going to be smaller than the input, right? So if, let's say, this is a CDF describing the height of the people, and I supplied, let's say, 8 feet, what's the probability of person being smaller than 8 feet? 1. If I supplied 3 feet, then it's going to be close to 0 and so on. So that's the nature of it. How do these functions look like? Well, they have general, if this is x input, then these functions would look like this CDF of x. And they will have a general shape like this, right? They would saturate at 1 and then 0. So some properties here, limit when x goes to infinity of CDF of x has to be equal to 1. That comes from the just physical interpretation. What does this function mean? Probability that you're going to be smaller than infinity is going to be 1, certainly. Likewise, limit when x goes to minus infinity, CDF of x is going to be equal to 0. Probability that you're going to be smaller than minus infinity is going to be equal to 0. There are other properties of this function. For example, that if let's say xa is greater than, or I should say b greater or equal than a, that means the CDF of b has to be greater or equal than CDF of a, which means this function is monotonically increasing function, right? So that's the CDF, and we use them quite often, right? They provide you complete description of the random variable. If I have a random variable and you provide me with CDF, I know everything there's to be known about that random variable. The second function that we use more often is what is called probability density function. And or PDF of x. Here, PDF of random variable x at a given value x0 is the derivative of CDF of that random variable at the point x0. This is capital. Small case when x is equal to x0. So this one is capital random variable. What is it? It's the derivative of this function, right? How do these functions usually look like? Well, they have some shape, right? And might be something of this nature. So this is PDF of x or x. They have some properties, just like CDF. Maybe I should put another property here, which should be obvious, that CDF of x has to be greater equal to 0 for every x, right? It has to be positive because it's probability. PDF of x also has some properties. PDF of x is also greater or equal to 0. It has to be positive, and that comes from this property of the CDF, because the CDF is monotonically non-decreasing function. It's always going up. Its derivative has to be either positive or as small as it needs to be equal to 0. Now, probability, the most important property of this one here is that probability that x is an interval from a to b is given as an integral from a to b PDF of x dx. So here we're attaching physical meaning to a single point here. If I specify x0, this value here is probability of x being smaller or equal than x0. But here, the physical meaning is in the area under the curve. So if this is an A and this is the B, this thing here indicates probability that x is between A and B. Let's see, like this one is closed, this one is open. Now, so and then there's what is called normalizing property from minus infinity to plus infinity. CDF of x dx has to be equal to 1. So this one gives us the probability density, right? It tells us if you look at this curve, the area where it bulges up, where it's the highest, that means that's the area where the most likely is the outcome of this random variable. If this, let's say I take this curve and I kind of bring it up this way, and then I stretch it, what does that mean? I'm reducing the scatter of this random variable. It will be taking values only where the curve exists. If I flatten it out, that means it will be taking values everywhere across this axis, right? So it tells you the density, it tells you where is the concentration of the outcomes of a given random variable. So these are the two functions that you would find very useful in characterizing random variables. They carry the same information. If I know the PDF, I can determine CDF. If I know CDF, I know PDF. PDF, I said, is more useful to us because it allows us to compute expected value of something, but that kind of goes a little bit outside of what I intended to cover. The third function that I'm introduced here is going to be complement of CDF. Right? Or sometimes referred to as CCDF of x. Right? So CCDF of a random variable x evaluated at point x0 is going to be probability that x exceeds x0. Right? So these are complement cumulative distribution function curves. A lot of times they're referred to exceedance curves. Right? Because they give you probability of a random variable exceeding given threshold. How do these guys look like? Well, they're complement of CDF. So if CDF looks like this, then your CCDF might look like this, right? X is the CCDF of this threshold here is 0. And the properties are complement of these properties, like CCDF of x when, limit when x goes to infinity now, of CCDF of x has to be equal to 0, because nothing is greater than infinity, right? Probability that you're going to exceed infinity is equal to 0. Limit when x goes to 0, minus infinity of CCDF of x is equal to 1. Probability that you're going to exceed something that's infinitely small is going to be a sure event, and so on, right? The completely opposite, I guess, complement properties to these guys. Now, in satellite communication, we already kind of introduced CCDF. When did we introduce the CCDF? When we talked about peak to average power ratio, right? Over there, we said, well, this peak to average power ratio of this waveform at a threshold of 0.1% is, let's say, 5 dB. So what does that mean? This is exactly what I have here. So let me do that as an example. So peak to average power ratio characterization. And in that case, it is common to give curves in a log scale, where you're going to have here CCDF of PA/PR, and here you're going to have PA/PR in dB. And the curve might look somewhat like this, right? Where this indicates these are the different thresholds, let's say 10%, 1%, 0.1%, 0.01% and so on. And then here you get some values. Let me just give the numbers. So let's say this is 5, 10, 15, and so on. So this would be a curve that would characterize the waveform, telling us peak to average power ratio in dBs, and what is the probability of exceeding the particular peak to average power ratio. So if I design my system with this threshold, then I have to back off my power amplifier by 10 dB, right? And then I know that 99.9% of the time I'm going to be within the linear range of my power amplifier, and I have to worry about it 0.1% of the time, whether it's significant, what do I do about it, do I clip before I amplify, and so on, right? But I have to find a solution for that, and what kind of effect does that have on the overall system. We're going to be talking about CCDF curves when we talk about probability of exceeding given margins. And this will translate directly into this story. You're gonna collect, let's say, rain statistics for Melbourne, Florida, and you're gonna say 80 millimeters per hour is exceeded in 0.1% of the time, right? So 0.1% of the time throughout the year, it rains with the density that exceeds, or rains with a rate that exceeds 80 millimeters per hour. So if I design my link, and I'm shooting for 0.1% reliability, my link needs to be able to handle the losses associated with 80 millimeters per hour rate, right? If I want to increase my reliability of the link, and let's say I want to design for 0.01%, then I have to find for 0.01% what is the rain rate exceeded in that case, and then I have to design my link to handle these kind of losses associated with this particular rain rate. So we're going to be talking quite a bit about CCDF curves. We're not going to do much, like in other courses, we're not going to do too much of the probability and statistics, but we have to understand how to interpret these curves, right? And interpretation of CCDF is just like I said here, CCDF over a given random variable and a given threshold represents the probability that a random variable is going to exceed that particular threshold. Okay. So let me go back to the slides. So here's how we see our satellite link. We saw that ultimately, there are a lot of components of the link budget, but ultimately this is what it boils down to. You have your EIRP on the transmit side. You have your receive antenna with, let's say, losses that are associated for mispointing and all that stuff. Then you have your free space path loss, which is a big guy on the block. You have to count that one. You take that into account. But that one is easy because we have a formula for it and it's simple to explain. And then you have additional component of losses, which we call atmospheric losses. We had them in the link budget before. I talked about clear atmosphere versus rain atmosphere and so on. Well, this is where we need to kind of disclose how you calculate these particular values. Now, the complication comes from the fact that this LA is a random variable that changes the conditions of the atmosphere, the position of the transmitter and receiver, and so on. And we have two thresholds here that are defined. The first one is the performance threshold. You have to say, okay, my link needs to exceed this performance threshold. In digital link, in analog links, that threshold is the carrier to noise ratio, right? And we specify, okay, I need to provide signal that exceeds this C to N. And then the second threshold is the availability threshold, which says I need to provide my performance threshold over this percentage of time. So when we talk about microwave links, satellite links, we say, okay, we want to have 99.9% availability, which means 99.9% of the time the link needs to be designed to take into account and to overcome whatever is presented by the atmosphere, right? So there's enough margin to do that. Now, that means that 99.9% of the time, the performance of the link needs to be above the performance threshold. Right? So those are the two things, and that's common talk in satellite, also in microwave design. You know, microwave design, the guys that do microwave hops and point-to-point links, they will talk about reliability 3 nines, 4 nines, 5 nines, and so on. Meaning how many nines do you have before in your reliability number. So let's say 4 nines would be 99.99% of the time is the link designed to open. These are the curves that are given also in your book. So this is how the author kind of characterizes these thresholds. He says here, these are atmospheric losses. This is this Ln. And then as the atmospheric losses go up, then this is the percentage of the time that this would happen. Let's say in this particular link, you have 0.01% of the time the losses exceed 8 dB, and for there the link becomes unavailable. Your performance threshold is so low that the link becomes broken. But that's the design decision that you make as an engineer, right? So that's what is important. He defines a gray area too, which is performance degradation, where you have a link, but let's say it communicates at a lower capability. And then here, the link was designed with a margin of 6 dB. So that means if anything introduces losses that are smaller than 6 dB, the link will overcome that. There will be sufficient power there, and the performance will stay degraded here. Now, this is the same kind of plot. It's just that now instead of these losses, you can translate them into the bit error rate, which is the principal measure of quality for the digital links, right? That's a raw bit error rate. How many bits are on the link before you do the coding gain and all the other improvements that you have. And here, you see, the threshold was designed so that the bit error rate is 10 to the minus 6, 1 out of a million bits. And then if your losses exceed 8 dB, which is close to 0.01% of the time, your bit error rate is going to be higher than that. I guess this arrow is in the wrong direction. It should be pointing downstairs. But we have performance met, performance degraded, and link not available. Usually, you know, you just you don't have the freedom to say it just degraded. You either work, it works, or it does not work. Now, there are many components that, what makes this difficult is there are many components that contribute to this random variable. There are many components of the atmosphere that change what those losses are. Fortunately for us, not all of them are equally significant. Here I have a list of 7 different reasons why there may be losses in addition to the free space loss. But as I said, none of them, most of them are not equally important. The most important guy on the block here for the frequency range that satellite communication systems operate is rain. Rain is especially in KU and KA band, rain plays a very important role. We actually do design around the rain. Other effects contribute, but you will see from calculations that the impact of these other effects is relatively small compared to the rain. So if you design to handle a certain percentage of the rain, chances are you're going to be able to take care of all the other effects as well. But let's just briefly review what they are. Atmospheric absorption, that talks about absorption of the energy by the atmosphere itself. You will see that, as you know, the atmosphere contains gases. Those gases have resonant peaks which are the frequencies at which they absorb the energy. If you happen to be operating on the frequencies that are close to these, you're going to experience a certain number of dBs per the length of the distance that you propagate through the atmosphere. Then there's a cloud, all the hydrometeors like cloud and rain and ice and all the stuff that is in the atmosphere. Then there's, of course, rain. There is what is called tropospheric scintillation, because our atmosphere not only that it contains stuff, but it's non-uniform, and non-uniformity kind of causes the wave to bend in one way or the other, and therefore that produces an effect similar to the fast fading in the cellular, or in the terrestrial propagation. The same thing can happen because of the variations in the ionosphere. There's something called Faraday rotation, which changes the polarization of the waveform. And if you remember, when we did the frequency plans, we reused the frequency and transmit on orthogonal polarization. So the polarization kind of hurts you. The loss of the polarization hurts you twice. It hurts you because you lose part of the signal on the polarization that you receive, and you also corrupt the adjacent channel because now you're not orthogonally polarized to the adjacent channel. Okay, all of these losses are frequency dependent, and in general, you know, the higher you go in frequency, more losses you would experience. That's not absolutely true, because there are some bands where, for example, oxygen absorption or high water vapor absorption is larger when it's lower frequency. We're going to review that. But generally speaking, the higher you go in frequency, everything that you encounter will cause additional losses. It's just the objects that you encounter become bigger relative to the waveform, and therefore they become much more important. And as I said, the way how we deal with this is we compile a history of the meteorological data, and we have tables that will help us understand what does the climate look at a particular place where we are designing, and then through some math that we're going to all go over, we want to calculate something that is called fade margin. And fade margin will be the part of our design as a guard for us that to ensure that we meet the performance threshold. So first, I'm going to go through all of them. I'm not going to, as I said, spend equal time for each one of them because they're not of equal importance. But I'm going to actually go through it, at least with one slide through one of them to explain what the effect is and what is its magnitude and why should we care and how much we should care about. The first thing that we have here is atmospheric absorptions. Now, it's not very clear because the grid is too strong here, but you see there are two curves here. One that goes like this, and the other one that is underneath. And they are showing us the absorption in the atmosphere. How much does the atmosphere absorb relative to the, as a function of the frequency. So on the x-axis you have a frequency in gigahertz. That's the frequency of the radio wave. On the y-axis you have attenuation in dBs per kilometer, right? Maybe not in this book. So it says zenith attenuation, so I guess this is the attenuation that you, okay, through the whole atmosphere, because it's a satellite book, not a microwave book. So if you go straight up, right, and go through the entire atmosphere, this is how much of an additional loss you're going to have in dB. So if I pick a frequency here, let's say this frequency, this is 20 gigahertz, and I look at how much I'm going to be attenuated going straight up. This is saying about half a dB of additional attenuation going straight up. Now, usually you don't go straight up, right? Usually you are talking to a satellite through a given angle. So you're going to say, well, this angle is, for the angles between 10 and 90 degrees, this is how I can calculate additional atmospheric losses. Whatever is the zenith and attenuation plus or minus 10 log of the sine of the elevation angle. So obviously the lower you go in the elevation angle, your path through the atmosphere becomes longer, right? Because the shortest path through the atmosphere is going straight up. But then if you're at any angle that is smaller than 90 degrees, then your length of the path through the atmosphere is going to become longer, and your attenuation is going to increase. Now, the one really, I would say, remarkable property of this curve, what you see in this box here is essentially the range of frequencies that we use in satellite communication. We don't go, I mean, this goes all the way to, this is 100 to 350 gigahertz, right? That's way above what we have conquered so far. We are in this box here, and there are some peaks that we see. The one that we have dominant here is the absorption that is coming from the water. Let me just explain what these peaks are. This is, what happens is you have the principal absorbent in the atmosphere is oxygen, oxygen and water vapor. Right? And oxygen has spectral peaks around 60 gigahertz, and then another one at 120 gigahertz, and water has absorption peak that is very significant for us at 22 gigahertz. Now, so generally speaking, those are not, around 22 gigahertz is not a good band for us to operate, especially over long satellite links. So what you see here are two curves. One is given for dry atmosphere, which is the lower curve where the water peaks are non-existent, and the other one is given for the atmosphere that has a density of 7.5 grams per meter cubed of water. Okay, so now how do you use this? Well, you're going to look at your link that you're designing. You're going to find the frequency that you're designing for, and then from this chart, depending on what your atmosphere is, you're going to be able to read what the attenuation for the atmosphere, for the link is going to be from the absorption in the air, and then depending on elevation angle of your link, you're going to add some additional margin based on this equation here. But typically, after all of this is done and said, you're about, you use about 1 dB for atmospheric losses, which is not that much. And you've seen the examples we talked about atmospheric absorption of 0.5, 0.3, point something dBs for the whole link, right? So that's the order of magnitude that you should expect for the losses. And just a comment, it's not a little bit side comment. There are in terrestrial world, since you're propagating over smaller distances, you actually you are using even these peaks. You try to communicate even in these absorption peaks. Like a good example would be what is called 802.11 AD. That's 802.11, like a Wi-Fi set of standard, but 802.11 AD is a 60 gigahertz standard, which means it is designed to operate right in this peak, the largest one there, that exists there. And the absorption that you get from in this case, oxygen, is bad if you're trying to communicate over large distances. But if you're trying to reuse your spectrum over and over again over short distances, it actually helps you. And then now you can buy 802.11 AD transmitters and receivers that allow you to communicate usually with, I guess, electronic devices inside a room. You can get the reason why this whole thing was standardized is to get rid of all the cabling associated with the cable TV, those coaxial cables and all that stuff that you have, you know, that makes your TV area so cluttered, right? And these are the frequencies that we're going to use for that, because they are propagating short distances. It's so that you can reuse them in almost every room of the house. So, you know, so since the spectrum is so precious, we're going to use entire axis, but not for all applications. So let me go to the next one. The next one is cloud attenuation. This one is I guess, very difficult to predict because there are so many different types of clouds. But fortunately for us, it's not very large. Typically, you have, you know, fraction of a dB of the losses just due to the propagation through the clouds. There are studies that show that it is frequency dependent and increases with temperature. But after everything is said and done, you end up with 1 to 2 dB for frequencies at the higher end of the frequencies that we use. It is considerably smaller the lower you go in frequency. So most of the time you just set something, some relatively small value to take them into account, and not worry too much about it. They're much, if you design to handle the rain, then your link is designed to handle the clouds as well. So now let's talk about the rain. That's the big guy on the block, and that's the one where we're going to spend the most time addressing. As it says in the first bullet here, this is the most significant component of your additional attenuation in C, Ku, and Ka band. And its importance increases as you move higher the frequency. So it's more important in a Ka band. It's larger in Ka band than C band. There are 3 basic steps how we deal with this. First, we look at our statistical data and determine what we call here exceedance curves, right? Or determine the thresholds of the rain rate exceeded at a given place where we're trying to design the link. So if I'm putting a link here in Melbourne, I would look up the historical data for Melbourne, Florida, and find out what is the rain rate that is exceeded in a given percentage of time. The percentage of time being my temporal threshold. The threshold for which I'm designing, right, to make sure that my link is up. The second one is there's a way how we can, depending on your frequency and polarization, how you can translate this rain rate into specific attenuation. Specific attenuation tells you how many dBs per linear distance you're going to lose. So typically you can say the specific attenuation is 2 dBs per kilometer. That means, you know, every kilometer that you propagate through the atmosphere, you're going to lose 2 dBs. And then the step here, the third step is, well, what is the length of the path that actually traverses through this particular rain, right? Even if it rains here, you know, it's not raining in Cocoa Beach, or it's not raining, you know, if you look at this path, only fraction of the path is going to be obstructed by the rain. So we have to have some statistical tables that will tell us not only the rain rate, but what percentage of the path, depending on its elevation, goes through this particular rain rate. And this is not something that you can determine deductively. You cannot sit in your office and speculate and come up with the numbers. This is something that is determined empirically, right? You collect tons of data over many, many years, and then you kind of compile this data, do statistical analysis of it, and determine the typical values and the variations around these typical values. These studies are done all the time. There are satellites that fly around and then send beacon signals that will help us, you know, do the characterization of the atmosphere and the losses that it exhibits in a given parts of the world. When it comes to rain, just a little, I'm not a meteorology guy, but just to honor what's in your book, there are two broad categories of rain. There's something called stratiform rain and convective rain. Stratiform rains are those rains where you don't know if it rains up or down, right? It kind of just rains, right? And these are of a relatively low rate. You know, they exist over large geographical areas, right? And they're not typical for places like Florida. They're typical for continental, let's say, East Coast and also West Coast. Like this is the weather in like Portland or Seattle, or places where there's a large area of rain of the small intensity. They are not of a grave concern to us because the rain rate is small, and even though it rains over a large terrestrial area, because our path is slanted, the relatively small portion of the path is obstructed with a rain rate of a relatively small intensity, so they result in a relatively small additional attenuations. What is problematic for satellite links are these convective rains that are raining over relatively small geographic areas, but the rain rate is really intense. And this is what we have around here and in many other parts of the country, where it starts when it's raining, it's pouring, and then that may cause the outages because the rain rate is of the intensity that increases the loss, increases the losses on your link. So if you design for these guys, you're going to take these guys into account as well, right? Because it usually does not happen that they're simultaneous, right? It really either rains or pours. So how do we characterize rain? Well, as I mentioned earlier, the principal two for rain characterization are what is called these CCDF curves or exceedance curves. This is an example of a such curve. I don't know for where maybe this is something I drew. This is the rain rate that is exceeded in percentage fraction of time that the given rain rate is exceeded, and then this is the actual rain rate. Rain rates are, you know, in the order of 20 to like 200 millimeters per hour. That's what we can expect. And as you move higher into the rain rate intensity, it becomes progressively less and less probable that you're going to exceed this particular rate. So in this case, for example, if I just follow this example, a rain rate of 80 millimeters per hour is exceeded about 2 times 10 to the minus 3 percent of time. There are several sources for this data. Over the years, they provide you different spatial resolution and time resolution, right? The time resolution is, you know, the rain, it never rains at a constant rate, right? So it kind of rains like this. And the question is, how do you sample this? Or in other words, how do you average this? And a lot of sources would average in 1 minute increments. Sometimes you're going to get them in hour increments, but most of the ones that we use for satellite design are in 1 minute increments. Principal source that we all kind of converge when it comes to these kind of studies is ITU, International Telecommunication Union, which publishes these curves. And if you go to the website of ITU, you can get these specifications. They usually go with, they usually hold the names ITU-R, R stands for radio, and then there is a number associated with specification followed by the year where that specification was compiled. So you can have, for example, ITU-R 867 2011 means that's an 867 specification that was published in 2011. The next time it is revised, it's going to carry so you can have the same specification with different years. We're going to go through some of them later when we start incorporating images into design. So there are two major approaches how we how all of these data are compiled. First is through what is called rate climate maps. and the other one is what is called rain exceedance curves. Rain climate maps are, I guess, a little bit simpler, but they're less accurate. They are extensively used in microwave design and I guess satellite alike, although exceedance curves are more common these days. But the approach here is as follows. The world is divided into 15 different climate regions based on the rain rate they experience. They're listed as A through Q. Now, if you look at A through Q, there's more. If you count all the letters, there's more than 15. Well, the letter O and letter I are not used. So you have climate regions A, B, C, D, E, F, G, J, K, L, M, N, P, Q, right? I and O are omitted for obvious reasons. I looks like 1 and O looks like a 0, right? So you don't want any confusion. Just like in your car, when you have a VIN number, there are no O's and there are no I's in that VIN number as well. Or 1s or 0s. They just say, forget about it, we're gonna remove them, right? And then for every given climate region, you have CCDF curve. And that's a CCDF curve that is given here. For example, let's take a look at our Florida. We're in a region, we're kind of here on the border between N and M. But let's assume we're in N. So if we are in the region N, this gives you the rain rate exceeded in 10% of the time. So 10% of the time, it's going to rain more than 5 millimeters per hour. In 0.1% of the time, it's going to rain more than 35 millimeters per hour. And then in 0.01% of the time, it's really going to rain with the rate 180 millimeters per hour. So 180 millimeters, so this is 180 millimeters per hour. So about 0.01% of the time, it's going to rain this much in an hour. Right? Now, these numbers look small, but take this and multiply by number of minutes that you have over the period of years. So we've all experienced this kind of rain. Right? When you step outside and it's just like a shower, right? And this is how the maps look like. I have focused here on the US, so you can see that we have a few regions, I guess. And you can kind of recognize that just by looking at the news that there are all different types of climates that we have here in the United States. They are based on the long-term averages, and the claim is that they are within the 10%, which used to be, and still it's okay for a lot of design work. Now, you have to be careful here because they are long-term averages. So what that means is you have to actually look at compile the long-term statistics before you can claim that that you met the specifications or not. Let me clarify that point. Let's say you are burdened to design a satellite link, and you design it using these curves, and your margins end up being, let's say, 7 dB. You build a link, it's 7 dB margin. You claim it's not going to be the outage time, which is a complement of availability, is not going to exceed 0.1%. But then the next year, the link is working and it's 0.2%. Did you fail? No. You have to have you have to compile statistics over several years to actually be to make sure that to kind of claim with certain reliability that you either met or you didn't meet the threshold. Because the next year might be the year of El Nino and it's raining much more than what was used in what came out of these particular CCDF curves. Alternative to the CCDF curves are these rainfall exceedance contour maps, they are, as you can see, more detailed than what CCDF, than those CCDF curves that follow the climate maps. The way how you, this is given in ITU recommendation P837-5, this 5 means 2005. I guess that's when I put this slide initially. Probably you're going to find, if you go and Google P837, probably there's one with a more recent number here. Now, what the recommendation gives you is, there's a problem, right? When you give the contour map, the data are two-dimensional, right? If you put the point on the contour and you give it a label, let's say this is a contour 80, then it's just one piece of data. You have to kind of specify it and then what threshold they're given. So typically these maps are given at 0.01% threshold, which is what is the 4.9 threshold. And then also if you open the recommendation, they actually give you a way how to interpolate these curves to a different reliability thresholds. And they give you methodology how to interpolate spatially. So if you're let's say in between, let's say this is an 80 and this is 70. So you're in between 80 and 70, how to get exact value there spatially, and then how to get temporally too, right? How to interpolate temporally. So you can say, okay, well, my link is going to be at this point, is between 80 and 70, and I need it to be 5/9. So there's some math in the recommendations that tells you how you actually get to these reliabilities from these curves. Right? In a lot of software packages that are doing these kind of things commercially, that are used for the design, they have this in the background. So the user would typically enter the parameters that we care about, like what is the reliability and what is the recommended, what is the reliability threshold, and based on the location of the Earth station, it will tell you what the rain rate you should expect at a given location. But just as a guideline, what I would like you to do is look up some of these. Just Google it. I think I have also posted it on the website. So on the website there might be a PDF document that contains this recommendation. You just look at it and you will see they're very, very good. They're very scientific and very. Not only do they give you significant scientific data, but they're also written by engineers. So they're very practical in how to use them. Sometimes they give you step-by-step algorithm saying, okay, forget the science, these are the steps that you need to execute to give you the particular result that you're looking for. All right, so a couple of examples here. So we're in Melbourne, Florida. It says, determine the rate exceeded in 0.1% of the time for Melbourne, Florida, using these two maps, right? Two approaches. One is the ITU climate map, and the other one is ITU exceedance curves. And the answers here, let's say, how do we get to these answers, right? If you look at 0.1% of the time, so we're here, and it says the rain rate exceeded in Melbourne, so we're in N. It says here 35.
It was 0.01 maybe?
0.01, so yeah, 0.01,
Yes.
sorry. So good, yeah, so I'm going to allow me to correct. So if you look at 0.01, in this case, so you would identify the climate, this is N here, and if you go N and 0.01, this would give you this 95 millimeters per hour. If you look at, however, where these curves are, it's not step-like. It doesn't, it's intuitively clear that the rain rate does not change as a step function, right? So the closer to the boundary is you're kind of getting closer and closer to the rain rate in the next region. So if you look at the rain rate in M region, it's 63, right? So 95 is probably somewhere in the middle, and then towards the end it's slightly lower. Also N, the 63 is in the middle, and then towards the edges it is whatever is in the adjacent region. So if I were to look at where this crosses, it crosses right above the Melbourne. So you would say, well, 95, 63, 90 plus 63, what would it be? 150, close to 160 divided by 2, around 80, right? And if you look at the climate maps here, they're more detailed. There are this contour here that goes like this. It goes straight above numbers, so it's the 80 contour. So in both maps would give you approximately the same results of 80 millimeters per hour. That's for just eyeballing, but as I said, if you happen to use the tools of the trade that are used in this kind of designs, they have the maps and interpolation methods that are embedded in them. So you will just type the location, the satellite, it would calculate the elevation and azimuth and the length of the path and all of these kind of things automatically, but you still have to understand how the things happen behind the scenes. Any questions on this? So where do we go from here? We went through the first step. First step is the characterization. We have to know statistically what happens when it comes to rain at a given location. The next step is going to be how we translate this rain rate into the margin that we need to incorporate in our design. And there will be some models that we're going to talk about next time. Okay, that's it.